In the course on fuel, refractory and furnaces, I had included few miscellaneous topics which are also important. So, some miscellaneous topics which I will be going to cover in the next few lectures. One is atmosphere in furnaces, atmosphere in furnaces, and second I am going to cover temperature measurements. Temperature measurements, because many a times temperature measurement is also an important issue and one should know the principle and operating details of temperature measurements. Third, that I will be including on electrical resistance heating. So, as such, let me first start with the atmosphere in furnaces. Atmosphere in furnaces. Now, I had always said that a furnace is thermal enclosure and is used to employ heating of the object to the required temperature. Now, in this connection, in many applications it is required that a certain specific type of atmosphere in the furnace should be maintained for doing certain special type of jobs. So, why we need atmosphere in the furnaces? Why we need a special atmosphere of the in the furnaces? Now, when I say atmosphere in the furnaces, then I mean fuel fired furnaces or electrical furnaces, because both are used for heating, and in many situations one does require a special type of atmosphere. So, why we need? The first reason, to prevent oxidation. To prevent oxidation. Now, this is particularly very much required when you are heating, for example, steel alloys below their melting point for thermomechanical processing or for heat treatment purposes. Then oxidation is important, because if you heat them in the atmospheric oxygen, then certain amount of oxidation will occur, and accordingly scale formation is there. So, either you remove the scale or you avoid the oxidation atmosphere. Another important function of the atmosphere, say to obtain a surface layer, to obtain a surface layer of carbon and nitrogen for special properties. For special properties, because you know the process is called carburization and nitriding. They are the two important case hardening methods where an appropriate atmosphere is created, so that the carbon and nitrogen of the atmosphere, it diffuses into the surface of the steel, and accordingly surface is case hardened. Third, for many semiconductor applications, or to produce semiconductor material, doping of alloying element is also done. With the doping, I mean that elements which are in very, very small concentrations are put in the atmosphere, and they are allowed to diffuse into the semiconductor material, and that is called doping. So, the third objective, to dope to dope alloying elements in semiconductor material. Now, fourth objective, we also carry out sintering. Sometimes sintering of carbides, it requires dry hydrogen atmosphere. So, sintering of carbides require dry hydrogen atmosphere. Also, as I said, many heat treating methods with the heat treating methods I mean annealing, normalizing, quenching, tempering, Mar tempering, Aus tempering and so on, to create a special microstructure in the steel for a special application. These materials also require certain special type of atmosphere, could be neutral atmosphere, could be reducing atmosphere, or whatever the case is. I am writing many heat treating methods require a special atmosphere. Now, naturally, the question comes how the various atmospheres are created. That is, how atmosphere is created. Now, essentially, an atmosphere means the presence of gases. So, when we say atmosphere in the furnace, we mean the presence of certain type of gases. So, the gases which are relevant for the atmosphere are hydrogen, nitrogen, then H2O, CO2, CO, they are alone or they are mixtures. So, depending on the requirement, for example, if we require a reducing atmosphere, we try to have a carbon monoxide or hydrogen atmosphere. If we want a neutral atmosphere, we want to have a nitrogen atmosphere, or if we want to decarburize the steel or the solid steel at high temperature, then we may like to have an oxidizing atmosphere, for example, CO2, or we would like to have an hydrogen atmosphere. So, when we say atmosphere means, that means you are creating or you are providing a mixture of gases or single gas. For example, if you want to create inert atmosphere only nitrogen over the piece of material which you are heating, that is what means the atmosphere. So, it is created say by combustion of propane, for example, C3H8, CH4, or by cracking ammonia. Now, for example, if we take say a combustion of C3H8, so we take C3H8 and if we completely combust, say for example, we take 5 O2 plus 3.76 N2, that is this much amount of air stoichiometrically if we take, then we are going to get 3 CO2 plus 4 H2O plus 5 into 3.76 N2. So, if we combust completely propane with the stoichiometric amount of air, then the atmosphere will consist of CO2, H2O and nitrogen. Now, in this stoichiometric amount, so what we need, say 1 mole of C3H8, 1 mole of C3H8, it requires 23.8 moles of air stoichiometrically. So, now if our objective is to create an atmosphere which is a mixture of CO, CO2, H2O and N2, then naturally what we have to do, we have to use air less than the stoichiometric amount of air. Now, if we use air less than the stoichiometric amount of air, as you recall from the knowledge of the combustion which I have given in the lectures 9 to 12, you know that amount of air less than stoichiometric will lead to production of CO, CO2 mixture along with H2O and nitrogen. So, now we can bring back those knowledge and put it here. If we want to create an atmosphere of CO, CO2 proportion, the proportion we have to specify, then by controlling the combustion and mixing with the right amount of air, we can create that particular CO upon CO2 ratio in the atmosphere. So, that means suppose if we want to create an atmosphere of say 1 mole of CO2, 2 mole of CO2, then what we have to do? We have to take air less than the stoichiometric amount of air, that is certain. So, for that case, if we take say C3H8, if we combust with 4.5 O2, 4.5 O2 plus 3.76 N2, then I will be getting CO plus 2 CO2 plus 4 H2O plus 4.5 into 3.76 N2. So, this is my atmosphere will consist of, if I take air less than the stoichiometric amount of air. Now, if for some reason I need only CO and CO2, then I must have a mechanism where I can remove H2O and nitrogen from this product for combustion. There are methods are available. So, second important thing to note that the reaction C3H8 plus 4.5, it is an incomplete combustion, and accordingly less amount of heat will be generated. So, lesser will be the amount of air we take, I mean lesser than the stoichiometric amount of air we take, more CO will form, but the reaction will be endothermic. So, one of the important requirement to create an atmosphere of increasing proportion of CO upon CO2, two things are required. One, you should have the amount of air less than stoichiometric, one, and second, you have to provide a external source of heating, because the reaction with less than stoichiometric amount of air, they are endothermic in nature, and accordingly external heating is required. And also it is required that the CO and CO2, they are, I mean, they are say analyzed and prepared for the particular atmosphere. So, in this particular case, what we will be having, say percentage CO will be equal to 1 upon 100 into 23.92, that will be equal to 4.2%. Percentage CO2, similarly you can calculate 8.44%, percentage H2O, that is equal to 16.8%, and percentage nitrogen, that is equal to 71.6%. So, this is say one of the method of creating of the different atmosphere using air less than the stoichiometric amount. Similarly, for this purpose methane can also be used, and accordingly the proportion of air can be adjusted depending upon the type of atmosphere that is needed. Now, in a similar way, for example, NH3, the 2NH3 can be cracked into N2 plus 3H2. So, you have an atmosphere which contains nitrogen and hydrogen. Now, based on this different proportion of CO, CO2, nitrogen and all these things, we can say what are the different types of atmosphere. So, we can now put type of atmosphere. Type of atmosphere. Say one, we have endothermic atmosphere. Endothermic atmosphere, and this endothermic atmosphere consists of mainly CO and CO2 ratio. That is, main CO upon CO2 ratio is higher. Now, as the name suggests, this endothermic atmosphere means the reaction at the time of conversion of propane or whatever the gas into the products of combustion which constitute the atmosphere, they are endothermic in nature. That means, by the name endothermic atmosphere, it suggests that the mixture of air and fuel, that means the amount of air is less than the stoichiometric amount of air, and accordingly one has to heat air gas mixture in a metal retort which is externally heated. If it is not externally heated, then the endothermic atmosphere creation is very difficult, because the reaction is endothermic in nature. Another one important thing is that external heating is required. One important thing is that external heating is required. For the reason already I have said, because these reactions are endothermic, and hence you have to heat externally, and that is an important thing. Second important thing is that the reaction product are cooled as they leave the retort. Now, why it is so? Because you know, as CO, it decomposes back to CO2 plus C at lower temperature. So, therefore, a abrupt cooling of the products of combustion is required in order to retain the amount of CO in the atmosphere. So, I will try to sketch a typical diagram. For example, if we have, this is the air fuel mix, we are having, this is air plus fuel mix, and it is surrounded by a gas fired furnace So, this is a gas fired furnace. This is a gas fired furnace. This is a cooler, and here say you have a burner, and this produces a flame. Here the products of combustion, they circulate, so that the external temperature of the air fuel mix retort is kept at a particular temperature. So, this is a burner. Then you need a system where you can supply air and fuel. So, you have here a system which is say air plus fuel. So, here you are supplying air and here you supply fuel. Now, at this site you have a sort of pressure regulator. This is a pressure regulator. And then you have a so called furnace, where now this furnace could be for heat treatment purposes, for heat treating or thermomechanical processing, or whatever the objective. So, this is the way, this is the endothermic atmosphere generator. Endothermic atmosphere generator, and these atmospheres, they are connected to the furnace. Now, another type of atmosphere is called exothermic atmosphere. Exothermic atmosphere. Now, the name suggests in the exothermic atmosphere the amount of air increases gradually from less than stoichiometric. If you go towards stoichiometric, then the heat will be produced, and accordingly they call exothermic atmosphere. And the closer we to the stoichiometric amount of air, more CO2 will be produced and less CO will be produced. So, that is why they are called exothermic atmosphere, and these exothermic atmosphere are produced by partial or complete combustion in a furnace. Now, say if we have, this is say a burner which is producing a flame, this is an outer, say, water jacketed furnace. This is here. This is all. So, this one is a water jacketed furnace retort. This is a burner. You are supplying here air, and here you are supplying fuel. Now, another important thing here, the catalysts are used. So, I am showing the catalyst. That is a catalyst. They are filled with the catalyst to catalyze the reaction. So, these are the catalyst. These are the catalyst, and here the products of combustion, they flow through here, here and here. This is the flow of products of combustion, and then eventually from here, say the output here, it is here. This is a system for atmosphere cooler, and then eventually it is taken into the furnace. So, this is how an exothermic atmosphere it works. Now, another is the, as I said, that the ammonia can be dissociated and to create an atmosphere of nitrogen and hydrogen. So, it looks like this. I will show you here the dissociated ammonia atmosphere generator. So it looks something like this. I have here a reactor, and this is the flow of dissociated ammonia line, and here I put on this side and this side these are the electric heaters, and this one is the dissociated NH3 line. Dissociated NH3 line. This is a furnace which is maintained at 950 degrees Celsius. So somewhere here we have an heat exchanger. This is the heat exchanger. So this one is a vaporizer, heat exchanger, here you have liquid NH3 inlet, and here passes through a valve system ammonia vapor. And this dissociated line is back to this particular thing. This is suppose the extra amount of NH3 is bleed off, and through a system of valves, this atmosphere line, this is the atmosphere line, which contains nitrogen plus hydrogen to the furnace. Now this one is the dissociation having with catalyst. So the whole thing is that you maintain a furnace at 950 degrees Celsius, ammonia dissociates, and that's it, you get this the atmosphere which consists of nitrogen and hydrogen. Now many a times we also need pure gas atmosphere. Now earlier we have seen the atmosphere consists of mixture of gases. So pure gas atmosphere, for example, we need nitrogen atmosphere. Now nitrogen is produced by liquefaction of air. And moisture is removed. For dry nitrogen production. Second, nitrogen can also be produced, nitrogen atmosphere can also be obtained from NH3 also. Now important point to remember in case of nitrogen atmosphere, that the dew point of nitrogen, dew point is -60 to -68 degree Fahrenheit, and the use of nitrogen atmosphere is, say, for sintering, brazing, and annealing. Then another atmosphere, for example, hydrogen atmosphere. Hydrogen atmosphere, you know, it's a reducing agent. So hydrogen atmosphere is produced from natural gas or by electrolysis of water. Electrolysis of water. Hydrogen typically provides a reducing atmosphere. Now you must know that hydrogen is very explosive and it requires very careful handling. Another important point is that many steel alloys are susceptible for hydrogen, and hence they may cause hydrogen embrittlement. So therefore, one should use it wherever it is required. It is also to be known that it is a very strong decarburizer. Say if you use for carbon steel, if you use hydrogen atmosphere, then C plus 2H2, it forms a methane. It is a very strong decarburizer and hence should not be used for carbon steels. Now it is mainly used, hydrogen atmospheres are mainly used say first for annealing of, say for annealing of say low carbon steels, electric and stainless steel, and stainless steels. It is also used, as I said earlier, sintering of carbides, sintering of carbide. So these are some of the say. Another say many times you require say helium and argon atmosphere. Helium and argon atmosphere. By nature, all of us we know that hydrogen and argon, they are inert, and their applications, for example, used for TIG welding, heat treatment of special high temperature, high strength alloys, and nuclear applications. Now I will tell you now some of the selected protective atmosphere, You can also consider the atmosphere which we are discussing. They are also protective atmosphere because they protect against certain things. Selective protective atmosphere and their applications. I will just make a table for you so that you get a feel the type of atmosphere, their composition, and relevant application. So I will put first of all an atmosphere followed by its composition, and in composition I will put nitrogen, CO2, CO, hydrogen, and methane. Then I will put another, that is the dew point. Remember, dew point is a very, very important in case of atmosphere because it is the temperature at which a gas begin to condense, and applications. Few applications I will give you, more you should consider the books and find out. So one atmosphere, it is a lean exothermic atmosphere, lean exothermic. Now lean exothermic, it has 86.8, the composition are all volume percent, 86.8% nitrogen, 10.5 CO2, 1.5 carbon monoxide, and 1.2 hydrogen. CH4 is nil. dew point is 4.5 degrees Celsius, and their application for bright annealing, of copper and sintering of ferrites. So this is one particular lean exothermic atmosphere. Now say another is, let us say, is a rich exothermic atmosphere. Rich exothermic atmosphere. The difference again in the proportion of CO2. So here you have 71.5% CO2, 5% CO2. In the rich exothermic atmosphere, nitrogen is 71.5%, CO2 is 5%, CO is 10.5%, H2 is 12.5%, and methane is 5%, and it is dew point is 10 degree. So its application are again bright annealing, of low carbon steels, silicon steels, and it can also be used for brazing. Sintering also one of the applications. Now third is one, say, dissociated ammonia. Dissociated NH3. Now this has 25% nitrogen and 75% hydrogen and nothing, and its, say, dew point is minus 50 degree C to plus 60 degree C, and is used in brazing, sintering, etc. Now still another atmosphere, they are the endothermic atmosphere. In the endothermic atmosphere, nitrogen varies from 40 to 45%, CO2 0 to 0.5%, CO is 20%, note that CO is 20%, hydrogen is 34 to 40%, and CH4 is 0.5 to 1%, and minus 10 to plus 10 degree C, that is its dew point, and this is used for hardening, carburizing, sintering, and several other type of functions. Another, say, important type of atmosphere, they are, one is the nitrogen atmosphere. It carries nothing except 100% nitrogen. It is a neutral wherever it is required for annealing is one of the purpose. Then hydrogen, again 100% hydrogen. It is a reducing atmosphere, and argon and helium, they are inert atmosphere. Having studied the different types of atmosphere, now let me address little bit about the heating of the protective atmosphere furnaces, because once you are supplying the furnace with the atmosphere, now heating is to be done very carefully. That means you can do, one is the indirect heating. You cannot heat now directly. Second, you can also heat with the radiant tubes. And third, of course, on the electric heating. But if you want to heat a fuel, then it has to be indirect heating. Now, the furnaces are of two types. One you have batch furnace and another you have a continuous furnace. Now, this particular diagram which I had drawn for you is a bell type furnace with a protective atmosphere. This is typically a batch type of furnace where you have electric heater as you are looking for, it heats the charge which is inserted into the furnace. So, the atmosphere enters in, that is the inlet, and here is the circulating fan, and this fan circulates the atmosphere above the or around the charge which has been put on a rack. This is a rack with the charge. So, this is how a sort of a batch furnace look. Now, similarly, you can visualize in a continuous type of furnace, the atmosphere has to be continuously in and it has to be continuously out because of the nature of the continuous furnaces. Now, this gas which is going out of the furnace, it is hot and it can also be used for preheating of the charge. So, batch type and continuous type. Now, the operation in this, both the furnaces are first of all filled with the atmosphere and the process is on. Now, a simple calculation will illustrate you about the velocity and volume flow rates. Now, for example, a continuous sintering furnace has 300 into 300 millimeter loading port and 300 into 250 millimeter unloading port. Because for a continuous furnace, continuously load it and continuously to unload it. So, from one cross section atmosphere will enter and another it will leave the furnace. Now, the protective gas pressure is 45 Pascal gauge. That means above the atmospheric pressure in the furnace. Furnace volume is 1.3 meter cube. Density of gas is 0.35 kilogram per meter cube. Now, assume contraction coefficient 0.65 and neglect friction. What you have to do? To calculate velocity and volume flow rate of gas. Velocity and volume flow rate of gas flow from the furnace port, and second you have to calculate volume flow rates if both the gates have flexible curtains of hydraulic resistance, take it 25. So, this type of thing we have already done when I was doing the fluid flow in the furnaces, and there you recall that the velocity of gas, I hope you must be remembering, velocity of gas that is equal to 2 into delta P upon rho. Now, by substituting the value of delta P and rho, the velocity you will be getting 16 meter per second. Now, immediately we can find out volume flow rate, say volume flow rate for loading port, that will be equal to CD into V into A, which is given to you a discharge coefficient. That will come out to be equal to 0.936 meter cube per second. You see that much amount of gas you will be requiring, and volume flow rate for unloading port, that will be equal to, same way you can calculate CdV into A. V is the same area, you know, it comes out to be 0.78 meter cube per second. Now, in presence of curtain, the curtain offers a hydraulic resistance. So, in presence of curtain, velocity V 2 into delta P upon, say, hydraulic resistance into density. If you substitute all the values, the V you are getting at 3.21 meter per second. So, now we can calculate similarly, say, volume flow rate when curtain is there. You have to multiply 3.21 into 0.3 into 0.3, and for unloading, volume flow rate for unloading port, that will be equal to 3.21 into 0.3 into 0.25. So, one will be equal to 0.29 meter cube per second, and another will be 0.25 meter cube second. What I have tried to illustrate, that the earlier lecture which I delivered on fluid flow in the furnaces, they can equally be used here also to find out what is the flow rate of the gas is required, what is the velocity of the gas which is there, as an information for improvement of the working of the atmosphere. Now, the another important thing which is here is so called instrumentation. Now, in the instrumentation, one requires measurement of CO, measurements of CO, CO2, CH4 and NH3. Now, the online measurements are available by using infrared analyzers or continuously analyzing the atmosphere. So, one type of instrumentation is the measurement of CO and CO2, and here the infrared detection technique is used to find out the percentage CO, CO2, CH4 and so on. And another important, as and when is required, measurement of oxygen. Measurement of oxygen, if oxygen is present, and for that solid electrolyte sensors are used to measure the oxygen content. And third, which is the most important in case of atmosphere, is the dew point measurement. Is the dew point measurement, and this dew point measurement I will discuss here. I just draw a sketch for you. The instrument which measures the dew point, that is, you have, let me draw the sketch. Say this is, say, from here the gas inlet, here we have gas outlet, and here we have, say, this is an outer enclosure, and this one is the resistance thermometer, and and this one is the, I will call this, put it here, this is the mirror. This one, resistance thermometer. Thermometer. This is a Peltier cell. So, this is the infrared source, it hits the mirror, and here you have the infrared detector. So, this is the infrared detector, Here infrared source, here is the gas inlet and there is a gas outlet. Now, a light beam, it strikes the mirror and is reflected from the mirror and detected by the photodiode. That means you have a detector and a source. So, a light beam, it strikes the mirror and is reflected. Now, if the gas passes, say atmosphere passes, and if some amount of steam or is condensed, or if there is a condensation occur, then accordingly the amount of reflected beam, rather its intensity will be influenced, and accordingly the temperature will be measured, and that is called the dew point. Now, mirror is also heated or cooled by a so-called solid state Peltier device. So, that is how a system for measurement of dew point it works, and in fact this dew point measurement is very important, because if the gas condenses during the process, then it is considered to be producing a hazardous effect. So, with this lecture, I think I have said sufficient on the atmosphere of the atmosphere in the furnaces, and towards the end of the few lectures I will give the references so that you can go and read further about the atmospheres in furnaces.